I've had a lot of questions about opcodes and operands and what can be there. You don't know what can be there. So you shouldn't try to do anything with it other than grab it. So if the page edge is there, you have a label and you have rules for validating labels, i.e. no odd characters. And what about should that work? Should you flag an error? Is it valid? Is that line valid?
Yes.
Yes. It is valid.
Oh, shit.
Valid? Yes. So you should be able to process. I mean, this is one token. This is one token. This is one token. And this is one token. This is a label, opcode, operand, comment. But wait, you might see 1, 2, 3 in quotes A, B, C. And the X on the end is not a valid opcode. Well, you don't know what a valid opcode is with your file parser. The file parser doesn't know anything about opcodes. So if there's something there, you take it. The question is, what distinguishes that as one token and the fact that there's spaces in there? If you didn't have the quote marks, then this would be 1, 2, 3 tokens, but they're quote marks, so it's all one. So you need to accommodate this with your code. So this is the problem I asked you to solve. I mean, I kind of gave you most of the rest of it, which is okay. I mean, you're just learning C++. But this is a problem you can solve, and you really don't want to find yourself in this situation where it's December, you're writing the last piece of this, and your file parser isn't working correctly. So rather than finishing up your project, you have to go back and edit and modify code that you wrote in October. Fix that first before you can do your assignment. You don't want to go there. So, okay. Any questions about this?
I do have a question.
Yes.
So if I have a comment on the first index, the first column,
Yes.
and what follows, it's supposed to be just one token, right? But if I have more like spaces in the comment on the first column, that should be just one token, right?
If there's a comment, so the comment might start here.
Mm-hmm.
The comment might start here.
So the problem that I'm having is when I have a comment and a space, it works. Like my tokenizer splits everything, and then if I do spaces, it does work. But if I do a tab after the asterisk, it breaks.
Oh, you have to fix that.
Okay.
You have to fix that. Wherever it encounters a comment out character, the rest of the line, you just take it and stuff it in comment. You don't even look at it.
Mm-hmm.
Don't even look at it. I would find the index of an asterisk, and then splice it, use the substring method, take the rest of that and just make it one token. Don't even look at it. And there's no reason to go down and start parsing what's in a comment. You just take it, put it there, and move on. Other questions? Yeah.
We can include characters in the
Yes, include the asterisk. Sure. So you're going to make a hand-in subdirectory, and in that hand-in subdirectory, you're going to make a PROG1 folder, and you're going to put all your files in the PROG1 folder. You're all comfortable with that? Everybody knows how to do it? Okay, good. Then one printout with your name and team number, all of your names and the team name on the front of it, and have your printout on Monday. No more questions. Yes?
So the M include will need a second right now, right?
I'm sorry?
If the hashtag M include doesn't have a second, like a file path, I should probably go in there, right?
Yep.
Yeah.
Whether you do it now or you do it next time, that's up to you. But yeah, that's going to be an error. Other questions? Okay. Yes?
So you said a printout over CZ and H file?
I want you to print out the H file and the .cc file. You don't need to print the exception file because I wrote it and I know what's in it. But you're adding things to the H file, so turn that in, the .h and the .cc file for your file parser. Also, it sounds silly, but look at this stuff before you turn it in. Use a monospace font like Courier and set the size so that the lines don't wrap. You have wrapping lines, it makes it very difficult to read. Typically, use Courier font in size 10, and that will get everything on one, reasonably small, but the wraps won't happen. Unless, if you've got a great big monitor and you type all the way across, then of course it's going to wrap, but you shouldn't do that. So, see if you can monospace font, no wraps. Names, team name on the front. Okay, good. Any final questions on that? All right, I'm assuming you're good to go. I'm anxious to see how you have solved this problem. So I'm going to go back and continue talking about assemblers. You guys have your sheets, right? We do have a few extras if you don't have those. All right, so what you have here is a listing file. This will be generated by the assembler. So what needs to be processed on the first pass? Well, the main goal of the first pass is to identify all of the user-defined symbols and give them an address. So that means checking each opcode entry. And if it is an assembler directive, you may or may not be able to process it here. So which assembler directives can you not process? On this page, what can't you do on the first pass? Sounds like a good test question. What can't you, which of the assembler directives? Well, what's the assembler directive? Start? Yup. EQU? Yup. Base? Yup. It is. RESW? Yes. Word? Yes. Byte? Yes. Reserve byte? RESB? Yes. Word? Yes. End? Yes. Of these, which can you not process in pass 1? Nobody wants to, yes?
Anything referencing any of the labels?
Okay,
Loads,
like which one?
the load.
Well, the load's not a assembler directive. That's machine instruction. But you're right, the one above it here, we got base delta. Well, what are you going to do with that? You can't do anything. Why can't you process base delta? What's that? You don't know where delta is. You can't do anything with that. Yep. There's one other category of these that you can't process yet. What about delta? Can you take care of that in the first pass? No, you can't. Why can't you do it in the first pass? Because it generates object code. You're not generating object code in the first pass. The final column over here where it says machine code, but it's really object code. 0000014 from delta. You can't do that in the first pass. The first pass does not generate object code. So what about alpha? Can you process alpha? Well, let me ask you this specifically. This direction, alpha, RESW100. It generates no machine code. There's nothing there. Does it do anything? And if it does, well, it must, it's there. What specifically does it do? How do you process that particular directive? Alpha reserve word 100. So do we not know, or we're just tired? Okay, good. I'm glad you told me. So let's clear this mystery up before we deal with pass 2. So the goal of pass 1 is to identify all of the symbols that are user defined. So user defined symbols are things like alpha, beta, gamma, delta, zeta. Those are user defined symbols. It's not a machine instruction. It's just a label that's used to tag memory. Reserve word allocates 100 words of storage space. But the actual mechanism by which that happens is you move the location counter down by 300 bytes. So notice the difference in address between alpha and beta. Between alpha and beta. Yes?
So the reserved word only takes 100 words, 300 bytes?
100 words is 300 bytes. Yes, because each word is 3 bytes. So 57 plus 300 in hex is 183. This takes no space in the object code. However, the declarations of delta, zeta, and eta, and theta generate object code. So those you can't do, but you can calculate the addresses that follow. So the goal is to get the address of everything and to build the symbol table. So what does the symbol table look like? Well, you've got key value pairs. So you have these entries, alpha, and the value of alpha is 0.00057. You have beta. So when you have memory references, for instance, let's see, where is, okay, line number, is it 12? 11, I can't line them up. But you have something like LDA alpha, or make something up, LDA alpha. And to encode this thing, you look this up in the symbol table, you need this information. The CPU doesn't know anything about an alpha, but it knows about 5-7. So this is just a stand-in for an actual address. So you build a symbol table with all the user-defined symbols. So we have S, R, C, H, base, and base is delta, and delta is 3dB. The EQUs are different. For all other symbols, the value is the address where it falls. EQU is used to define the value yourself. You're saying base is equal to, or BSRCH is equal to, so you set it explicitly. Questions about this? So it's always the address where the label occurs, unless it's an EQU. Then you're manually setting the value. That's what that EQU is for. You set it yourself. Yes?
So is base supposed to be in the label column?
It's an assembler directive. It's an assembler directive. What base does is it turns on base mode. Base addressing mode, which we talked about in September. You may have forgotten about it. We will revisit. But you have base versus PC relative modes for addressing. Okay, so the process for passing line. You go through a line at a time. The first thing you do, you have a starting address that goes in the location counter. It's a variable to keep track of the current address. So you have the start opcode, which is actually an assembler directive. Start at this address. Start at 0. So you set the location counter to 0. Then, with each passing instruction, you look to see how much space it will take in the object code. Well, the assembler directives, EQU, don't take any space. They just build the symbol table. Therefore, the first how many lines has address 0? 1, 2, 3, 4, 5 lines have address 0 because there's no actionable instructions in those first lines. Then the first one that actually does something, LDB, that's a valid machine instruction. It's format 3, therefore you increment the location counter by 3, and the LDS #3 command falls at address 3. You all with me? Okay. And then 6, and then A, and then E. So you increment this location counter by the size of the instruction that precedes it. By the size of the instruction that precedes it. So the starting address is always going to be the same address as your first instruction. Questions about this? All right. So the last column on the right, we have machine code. So I want to go ahead and talk about the executable format. So this executable format, the format of an executable or an object file, is based on this made-up architecture, but it's actually pretty good because it kind of mimics what's really going on. Alright, so I want to look at the format, and then I'm going to pass out the handouts here for you guys. So, we have object file format. So, at first you have a header record. So in column 1, you have H to designate that it's the header record. In columns 2 through 7, you have the program name. And then in columns 8 through 13, you have the starting address of that record. Oh, I'm sorry, the program. It's the header. And then in columns 14 through 19, you have the length of the object code. In bytes. And of course it's in hex. Okay. So, it might be helpful if I pass these out so you can see what this looks like. Let me just do this. So I'll redistribute them back if you don't have one. Okay. So the very top of this page, I have numbered the columns for you. So the last entry there is column 69. You see that? There's nothing in it. So we've got 1 through 10, and then 10 through 20, 20 through 30, and so on. So this is just labeling the columns to make this easier. So the first line, this is the header record. Column 1 is an H. The name of the program, PROG. Now this goes with the last handout, the listing file. So the first thing is the name of the program at the start assembly block. PROG, and then columns 6 and 7 are blank, but the position matters, so they're just left blank. Then columns 8 through 13 is the starting address of the program, and of course that's 0. 14 through 19. 14 through 19 is the length of the object code in bytes. So how long is this program? What's the length of this thing? So it's FA2 in hex. Where did that come from? It's the address after the last instruction. There is no instruction at FA2, it's after the last instruction. So if you started at 0, you assembled everything, then the address and the location counter at the end of this process is the length in bytes. That makes sense, doesn't it? Okay, so the next piece. The text record. So this is the executable code. Text records. Okay, so column 1, there's a T. Column 2 through 7, starting address. of this record. Well, the first one's going to be 0, of course, but not all of them are. It'd be silly for every line of this to have the same address repeated over and over and over. No, it's the address of this record, which is this line. So there's some implications to this that are important. Length of this record in bytes, and of course again text decimal. And then columns 10 through 69 is the actual code. So this is the text record. So this is what an executable file looks like. If you were to open up an executable and look at it through a hex editor, for instance, inspect it, this is what you would find. So I want you to compare with these two printouts here. See if we can identify what's going on. This first record, T, and then we have 2 through 7 is the starting address, and it's 0. Everybody see that? That's the first executable. Then we have the next entry is 8 and 9, and this is the length of this record. Well, what's the length of this record? What's the length? 1B. The 1B. Okay. So now we have 6923D8. Over here, our first instruction, 6923D8. So there it is. And then we have D6D0003. That's the next instruction. Line it up one after the other. And the last one we have is 75203C. And in the ends there's at line 19, the pound sign alpha, 75203C. That's the end of the line. So that instruction is LDT pound sign alpha. Okay, so that is all that fits on that line. Now, could they have squeezed some more in there? Not really. So notice here, that's at address 18. That's at address 18, and the next address after it is address 1B. That's the length of the record. That's where the 1B came from. You see that? So that's line 19. That's the address after the last record is line 19 is 1B. And that, if you look at columns 8 and 9 in the first text record, you have 1B. That's where that came from. Everybody find that? So this record, the text record, the 1B at 8 and 9. You see that? Okay, that's the length of the record. So, as we said, if you start at 0, then the line after the last record is going to be the length in hex. Okay? So how many bytes is that? In decimal. In real numbers. What's 1B? 27. Yes, now you can go and count the bytes. You can count the bytes. So we went to the 3C there, so you can count them. So we got 3, 6, and 4 are 10. I went to 9F now. The one ending in 9F, the third line. I went 3 and 3 are 6, and then the 06100F 9F. That's 4. That gives me 10. So you can count them. Count them and see how many windows. Okay.
Say that again?
You can count them. So looking here, we have 6923D8, that's 3 bytes. Each 2 digits of the machine code is 2 bytes. 2 hex digits is 1 byte. So 69's a byte, 23's a byte, D8's a byte. There's 3 bytes there. And the address in the line that follows is address 3. That's 3 bytes. The next one, 3 more bytes, that's 6. The next one, that one's longer. You see it ends in 9F. That's 8 hex digits. It's 4 bytes, so that one is 4 more is 10, which corresponds to the address of the line under. So that's just the number of bytes and hex that are on this record. Okay. Now then, so when we fill up the line, we move to another one. So notice we have 1, 2, 3, 4, 5, 6 text records for this little bit. The M records we'll talk about later. You can ignore those for now. The M records are there, you can ignore them for now. So, okay. Now I want to call your attention to what happened with the short line, the fourth text record. We've got T and then 0, 0, 0, 0, 5, 1, 0, 6, 3B, 2F. You find that one? Why is that one so short? Well, it's the end of the executable code, but there's more code to follow. So that last record, and I'm looking at this short guy here, the short one. If you look at the code on the end, you can see what it is. And you can see the 4F000. You guys find that? That's the last instruction in the R sub. Okay, but there's more code to follow, so what's going on here? That one started at address 5.1. So why didn't we keep going? There's more stuff. So we have alpha, beta, gamma. Alpha, beta, and gamma. They're not here. There's nothing here. No alpha, beta, gamma. Nothing in the code. Notice the address of the next one that follows. So the address, the one we're talking about, is 5051. You all see that? See where I am, this short line here, the fourth one of the text records. 051 is the address. Do you find that? And that, the address, of course, is in columns 2 through 7. So that's the 51, that's the address. The next address is 3DB. Everybody see that? Okay? So explain to me what's going on here. We went from address 051 to 0, I'm sorry, from 051, and the next record is 3DB. What happens is this. You have these storage allocation directives that don't generate any object code, but they change the location counter. All right? So in other words, we ended that record because the next instruction or the next object code is going to be way down in memory. We need to skip memory. So we need to start a new record so we can start at a new address. However, these three, alpha, beta, gamma, don't add anything to the executable code at all. Therefore, what we just need to do is start a new record at the address after those. So the first record starts at 5.1. The next one starts at 3dB. So essentially, it tells the computer to just leave that memory blank and go further down and start the next record. So this is how you reserve memory that's uninitialized. Now, if you had a declaration where you initialized memory, then you would have to have all of that memory in a text record. So consider this scenario. You want to declare a chunk of memory for an array. You want it to be 1,000 bytes. If it's uninitialized, you just declared it. Then all you do is reset the address further down, and it takes no space in the executable. If, however, you initialize it to 0, you have 1,000 bytes worth of zeros that go in the executable code. That eats up a lot of space. So if you initialize variables, it takes more space than if you do not. Because the value you put has to be here. Questions?
Do we assume that as a variable or just as a chunk?
It's just a chunk of memory that's left blank. So here's the scenario. If we draw a picture of a memory map, right? So here's a text record. We're going along and filling this all in. End of record. And then we have another text record. We're going along and filling this all in. One after the other. Now there's a storage allocation directive. With a new address. So the last one ended here. And the very next line says start filling in memory at this address. So you've left all this blank. You haven't touched it. You haven't done anything with it. You haven't looked at it. You just start down here. So what's in memory here? Well, who knows? Nobody knows. But the point is it takes no space in the executable for the next record to start down here. Questions? So this is one issue I frequently hear from students. It's like, but wait, uninitialized memory, what does that really mean? When you declare a variable but you don't initialize the memory, what does that, how does that work? What does that mean? That's what it means. Now you can't do this. You can't do this in Java, but you can in C++. Int x. You don't make an array of size 100 integers. What does that do? On the stack, you get the stack. Is there anything at x1? Suppose I print x1. What am I going to get? Whatever was in memory there. This is the mechanism how it works. So when you have uninitialized memory, whether they're variables or they're arrays, this is the mechanism by which you jump to a later address. Also notice you have all of these text records that can't exceed column 69. Okay, this is not a lot of space. So this first text record, which is as long as any of them, follow. This first text record is as long as any of them, and it only goes down to the 3 sets 1, 2, 3, 4, 5, 6, 7, 8. That's 10 lines. 10 lines in one record. So if you have 1,000 lines, how many records are you going to have? Well, a bunch of them. So doesn't this seem woefully inefficient? Was there any reason to split those first three text records? I mean, it's contiguous memory, right? You know, one after the other. Is there any reason to split it into three lines? Couldn't we just have it keep going? I mean, the computer doesn't have any concept of page size. Does it matter to the computer if a line is 500 characters long? No. It doesn't. So why three of them? Anybody know? So if you're doing 8 to 10 instructions per record, and you have thousands of instructions in your executable, how many records are you going to have? Plus, there is some overhead associated with doing this. What do you have to deal with? You've got the T, the starting address, and the size in hex. All right, so if you have 3 records, you have that 3 times. If you have 10 records, you have it 10 times. Not a lot of space, but that adds overhead. So why do it? Anybody have a sense of why you would do this? Not so much, huh? Okay. Well, the computer's memory is a lot like a hard drive in the sense that it gets used a lot. So you load a program in memory and it goes here. Then you load another one and it goes here. And then you load another one, it's a small one and it goes here. And then you do another one and it goes here. Now you have a big one that goes here. And so on. Okay, now your memory's full. But this one's finished. And this one's finished. Now you need to load another program, but this piece isn't big enough. But this plus this is big enough. If somehow you could combine this space and this space, then it would be big enough. If this isn't big enough, what are you going to do? You need to load and run a program, and this is the only chunk of contiguous memory you have. It's the largest one you have, and it's not big enough. Now what? So this is an operating system question. I mean, you could think, well, okay, I could, defrag memory the way you defrag a hard drive, just move things. But of course, it's not that easy. If you decide to move something like this, move this back up so that the space is at the bottom, what would be involved in doing that? You want your gap here, so this is now a contiguous chunk and it's big enough. Could you move a running program? Well, you could. There's not a very good solution. Why not? You've got all those memory references. All those memory references. And at runtime, they have real addresses in it that you would have to change. For instance, looking at your output here. This one. The instruction at line, let me find it here. I can't line these up very well. Line 11, plus LDS at food. Okay, it has an actual address. You see the F9F? What's the address of food? F9F. Okay, if we move food, then not only do we have to move food, we have to change the machine code for that instruction because the address is wrong. So moving something in memory is really not on the table. So that's a lot of work to do. So instead of doing that, then we have a different strategy. I have a whole bunch of little bitty text records, and I can put them anywhere I want. Wherever there's a hole, I can put them. Does the computer care that these are in separate chunks? No. So when it's time to read an instruction, you read the starting address in the text record and you go there and grab it. So it's much, much easier to accommodate many little pieces in memory than several big chunks. Lots of little pieces works better. And so that's the strategy, and that's the reason for the text records. Again, this is what real systems do. They're Unix utilities that you can run that will diagnose or give you statistics on your executable. So the last time I did this class, I did an analysis of the final product, which was the assembler. So most of the students had somewhere between 1,000 and 2,000 lines of code altogether. And I ran the analysis on that, and guess how many pieces there were? Depended on the code, between 200 and 300 separate chunks. Between 200 and 300 separate chunks. And they are analogous to these text records. This is how it works. It's easy for the computer to manage a gazillion little bitty pieces. Humans know this would be unworkable. But thankfully, the computers handle these kinds of tasks very, very easily. You know, that's how the internet works too. I don't know if you guys are really familiar with this or understand the low-lying protocols, but when you are working on a website, say you go to Amazon and you want to buy something, or you're doing research for a project and you're looking things up, what you do is you send a packet to a server. It looks like you're connected, but you're really not connected. You're never connected. And they've gone to great lengths to make it look like you are, but you're not. So you send a request to Amazon to find, I don't know, what's something they have a zillion of, cheap watches. They got a zillion of those. So that you're going to get back something that could be many, many, many pages. Well, they're not going to send you one page intact, all in one piece. They're going to send you packets, little bitty pieces. And your browser will take all of those pieces and put them together and display the page. It's as if, suppose you're going to write a novel and you're going to send it to your publisher. The novel's 1,000 pages long. Well, you use a postcard to copy the novel. And how many postcards would you end up with? Well, many thousands of them. You drop all those in the post office box. Well, for people, that's ridiculous. For computers, it's the best way to do it. Having small pieces on the internet makes routing much, much easier. Having small pieces in memory makes it much, much easier to use the memory to the fullest. So now it isn't how big a contiguous chunk do we have? It's, do I have a piece this big somewhere? And the answer is almost always yes, I do. So you can use the memory more efficiently if you have lots of pieces. Questions about this? Anybody? Yes.
So what is one of these you gave us the text file, or the text records, or?
The text records are on this sheet. And these are the lines that start with T. So the first one, H, is the header.
And that's just the file, right? This literally is not
This literally, starting with the H and ending with the last zero, this is what an executable looks like. This is actually an object file. It is executable, but it's not linked and loaded. Well, what's the linkage? Well, that's actually the end records, and we can talk about that. We're going to cover it in greater detail. But there are certain places where you have to modify code. And that's what the M record is for. What do you have to modify? What you have to modify are hard-coded addresses, i.e. the format for instructions like I mentioned a minute ago. This one instruction here on line 11, plus LDS at foo. It's 4 bytes. It's got an actual address there. So at runtime, when you load the program, a request is sent to the operating system for a place to load it. You can't have address 0. It's a relocatable program. So the operating system will give you an address where this can load. So you have to add that address to all of these memory references so that you have the actual physical location of where this foo is at runtime, because it will be different every time you run the program. Questions? Anyone? Okay. So, I'm not sure I have enough time to dive in on pass 2. I don't think that's going to go. Let me finish this, please. That's the text record. The modification records we will talk about later. Then the end record. The end record. So the column 1 is E. And then 227 is the address of the first executor. And as you can see here, it's all zeros. Well, that's the address of the first executor. Questions? All right. So if you were given one of these, could you do this? If I gave you one of these and the rules, could you do this? Sounds like a test question. You know, last semester when I did this, they wrote an assembler, and all this is directly related to the assembly. All right, well, I want to talk about, I want you to learn things beyond what you're doing for your programming projects. So this is kind of how it really works. They have simplified the machine. The author of this book is the department chairman, actually. And the criticism leveled against this text is the fact that this isn't a real machine. Well, thank God for that, because mastering a real machine would be very, very difficult. But the essential concepts are the same. The essential concepts are the same. So the goal here is to teach you how this stuff works. And so, yes, it may seem like, wait, we're doing a programming assignment on file parsing, but now we're just going on and on about text records and end records and modification records, and do I need to learn this? And the answer is yes, you do. So we're going to be talking about assemblers for the next little while. And this is a major chunk of the course because essentially, whether you're writing in Java or you're writing in assembler, the machine can only execute machine instructions. So you get to this level no matter what you're writing in. So that makes this environment really important to study and learn about. So we're not done with this yet, but we are going to cover some more. But as we go forward, please try to at least understand what's going on as we do this, because you're going to see this material on the test. So, questions? Okay, I'm going to stop. Everybody seems kind of overwhelmed and preoccupied by the program. We're 15 minutes shy. My big problem seems to be I talk too long rather than too short. So I'm going to let you guys go 15 minutes early. You might take this chance to get together with your team and make sure the game plan to get this tied up and put to bed is in